Welcome to the next video on vine copulas. Now, the last time we talked about structure and how you could have a number of different structures for a vine copula. What I'm going to do this time is talk about how you can actually find out what the structure of the vine copula should be. So fitting a vine copula, the first thing you want to do when you fit a vine copula is try and work out what the structure of that vine copula should be. And as we saw in one of the earlier videos, the potential number of structures that you could have is theoretically vast. I mean, you've got 10 variables, you're into the hundreds of trillions of potential structures, which is not exactly workable. So you need some sort of way of getting around that. So what do we mean first when we're talking about finding the structure of a vine copula? So for a D vine, we're looking at trying to work out what the order of the nodes in the chain should be. For a C vine, what we're looking at is trying to work out which is the central node and which are the other ones, the ones that are connected to a central node. For an R vine, then you've got all sorts of different shapes that you could have. And in theory, it could be rather complicated if you wanted to do it exactly whilst finding out what was the absolute best fit for the copulas that you were using. Now, because it's difficult to do exactly, there are approximate approaches which have been developed instead. And the one I'm going to look at today is based on the one described by Disman et al. The paper there is at the bottom of the screen. And what they propose is a sequential approach. Now, it uses graph theory, which we talked about last time, and it is similar in the way that it works to some of the stuff that we did on decision trees, if you look at the credit videos that I did on those. And there are a couple of important aspects or terms which allow us to do this. The first concept that we need to explore or get comfortable with is the concept of minimum spanning trees, and the second is greedy algorithms. So first, minimum spanning trees. If you remember, an R-vine is a tree with all nodes connected by a unique path with no cycles, and if you've got however many nodes you've got one less edge connecting them all. Now, a spanning tree is a tree which contains all of the nodes of a graph. So you could, in theory, have a graph which contains two disconnected trees. A spanning tree is a single tree connecting all of the nodes of a graph, as we have in the diagram in the bottom right of the screen. A minimum spanning tree is a spanning tree for which the sum of the edge weights is as small as possible, or if we're thinking about it in vine copula terms, where the sum of the absolute correlations is as high as possible. So what we're trying to do is we're trying to create something where the nodes which are joined are the ones which are most closely related, and we get a structure which reflects that. So how do you find a minimum spanning tree? There's several algorithms which exist, and I'm going to cover a couple of them today. Most of them are what are known as greedy algorithms. Now what this means is that they are, as I said before, they're sequential, and they concentrate on finding locally optimal solutions. So this means that they'll try and find what works best for the particular part of the tree they're focusing on, but at no point do they look at the tree that they have created overall and look at whether it's globally optimal. Because if you're trying to find the best global solution, that's complicated. Trying to look at the best local solution and then move on to the next local solution and try and make sure that's best as well, that's much more tractable. So if we're doing this for vine copulas, the algorithms that I'm looking at, they all start by calculating all of the possible pair correlations, which isn't as bad as it sounds. For this, I use Kendall's tau. Kendall's tau is a rank correlation coefficient, and it's particularly well suited for dealing with copulas. I mean, rank correlation is how you should think about correlation for copulas anyway, because copulas essentially join the order of the observations rather than the value of the observations. And Kendall's tau does have quite a sound theoretical basis for this. It gets used directly in the calculation of parameters for at least two Archimedean copulas, and also if you're looking at elliptical copulas as well, Kendall's taus are often used there as the starting point for finding the correlations in those structures as well. So here are the two algorithms that I'm going to look at. The first is called Prim's algorithm, and don't worry if it's not entirely clear what's going on here, because I will be doing some examples, and the examples will hopefully make it a little clearer when we work through some of these in practice. So Prim's algorithm anyway, choose any node and then find the node with the highest correlation to that first node and connect it with an edge. Then find the node that has the highest correlation to one of the first two nodes and connect it with an edge to that node. And you just keep on doing that, making sure that you don't make any connections that create a cycle. And you work through all of the correlations that you've got from the largest to the smallest. And if you haven't got a fully connected tree by that stage, you go back to the start and you start working through all of the correlations that you missed out first time because you couldn't connect them. And you keep on doing that until all of your nodes are connected. The second algorithm is called Kruskal's algorithm. For this one, you order all potential edges, so node pairs, by correlation. And you work through connecting pairs of nodes, starting with the highest correlation and working down. Now, this sounds like Prim's algorithm, but the difference is not everything needs to be connected to your first pair of nodes. So if your highest correlation is between A and B, connect those. If the next highest between C and D, you connect those. And it doesn't matter that at the moment they're disconnected, because you keep on working down, adding connections until they eventually do get connected. So you continue through all the nodes, ignoring any connections that would create a cycle, and you continue until all the nodes are connected as a single tree. Now, there's another algorithm which is similar to this called the reverse delete algorithm. And it's similar in that it starts from the other end. So it starts with a fully connected graph, which is cycles and everything. So every node connects to every other node, and then works through by deleting edges that create cycles, and it deletes the ones with the lowest correlations. And it continues until you are left with a fully connected tree with no cycles in it. So here's the example which I do in Excel, and I've got 120 months of equity return data covering one world equity index, 5 country equity indices which I've labelled A to E, 5 banking stocks, one from each of the same countries labelled A to E. So that gives us 11 return series in total. And what we'll see from the results is it kind of demonstrates the international nature of some of the banks and the national links of some of the others, and it does give a good indication of how banks or stocks and markets and a global market might be connected. It's also interesting that the algorithms give slightly different results. So they're both good, but at least one of those must be globally suboptimal. So it just shows you that it can give you stuff which is plausible, which is useful, which is a good starting point, but it might not necessarily be perfect. So here's my return data running from columns B to L. Each of these is 120 observations for each of those 11 data series. And what I'm wanting to ultimately end up with is the Kendall's tau for each of those pairs. And it is not straightforward. So Kendall's tau is a pain in the neck to calculate. You have to look at, if you've got two asset classes, you need to look at each pair of returns within each asset class and compare it with a pair of the returns in the other asset class. So what you're trying to do is you're trying to say, for each pair of returns, have I got, say I've got returns in period 1 and period 2 for assets A and B. If the return in period 1 is higher than the return in period 2 for both asset class A and asset class B, they're said to be concordant. If the return in period 1 is lower than the return in period 2 for both assets A and B, then again they're said to be concordant. But if the return in period 1 is higher than the return in period 2 for asset class A, but lower for asset class B, then they're said to be discordant, and vice versa. So what that means is that I've got this table here which has 120 rows and 120 columns, allowing me to compare each pair over each time period. It's 120 rather than 119 because I'm starting by comparing each one with itself. So, and ultimately I want to do that for every pair of asset class as well. So you end up with a lot of numbers. So how do I do that? I do it with this formula here. So the first thing I'm doing is I'm creating a lower triangular matrix. What this means is that when I add up all of the observations here, I'm not double counting anything. So I'm saying if your column number is greater than your row number or equal to your row number, it's equal. So I ignore all the ones where I'm comparing something with itself. And then what I'm doing is I'm saying, look at your first time period, and that is defined by the, say the column number 1, or the row numbers rather, so the red square, and deduct from that the return in the second time period, and that's given by the column number in blue. And you do that for asset class denoted by EF4. And we'll see later that I cycle through all the asset classes. So I've got the difference in returns there. Then I do the same for the second asset class. And I multiply those together. Now the thing is, if I've got concordant returns, so they're both higher or they're both lower, I'll end up with a positive number. If I've got discordant returns, so one's higher and one's lower, I'll end up with a negative number. So if I do that calculation, and then I take the absolute of that calculation and divide the absolute of that calculation into that first calculation, I'll either get +1 if my returns are concordant, or I'll get -1 if the returns are discordant. Now, this example here, you'll see I'm looking at an asset class compared with itself. And clearly all of the numbers are concordant, so I've got perfect correlation. So the concordant pairs are the ones where if I sum over everything, I get a value of 1. The discordant pairs are the ones where if I sum over everything, I get -1, and I take the negative of that to get a positive number. And Kendall's tau is concordant less discordant divided by concordant plus discordant. So these are the results, and this is how I get them. So EF and EG, these are the numbers which tell you which return series to look at. And as you can see here, I'm setting it such that I'm looking at the first asset class compared with the first asset class. And I'm doing that by asking the formula in EF4 to offset from EF6 down by 1. So that gives me a 1. And also the formula in EG4 to offset by 1 as well. So that tells me that the column I'll be looking in will be for the first asset class, and the row I'll be looking at will also be for the first asset class. So if I replace that 1 in EH7 with a number 2, then EF4 would now be a 2, and EG4 would now be a 1. So that would mean that my correlation, rather than being perfect as it is in EI7, would now be a sensible number. So how do I get it to insert a 2 into EH7 without doing it manually? And that's just showing actually the correlation that I'm returning from O3 from that calculation. So how do I substitute those numbers into EH7 without doing it manually? Well, I do it using the table function. And the table function, what it essentially does is it says put each of the following numbers in column EH into EH7 and then give me the result, which gives me this whole string of correlations for every particular pair. And then what I essentially do is I say, if my column number is higher than my row number, I don't want to see anything. I only want to see stuff if my column number is less than my row number. And you'll see there that once I've got correlations noted all the way through, the labels next to them only appear for those situations where, again, it's essentially a triangular matrix, to make sure I'm not double counting anything. And the difference between the two is this is my first variable, this is my second variable. So In this situation, if I'm looking at row 18, I've got the correlation, Kendall's tau, between the world and country A is 0.876751. And this is just a matrix which I put together which actually pulls all this information together just so I can eyeball it. So I don't actually use this matrix for anything. It's just so I can look at the numbers and see, does it look sensible? And it's calculated by using the offset function as well, offsetting those results by the row and the column to pick out the relevant correlations, relevant Kendall's tau. So the summary correlations, I group them all together. And the way I do this is first by saying if one of those cells was a blank, so I didn't want anything in it, then just give me the same number that you had in the cell above. If there's something in there, so it's changed, increase the number by 1. This is just a count going from 1 up to whatever. And this is a lookup of those numbers in the first column. So this tells me how much I need to offset by to pick up every single correlation. So if I offset the list of correlation numbers by that number, it will give me the correlations. And the same formula gives me the labels, whether it's, so first one is between world and country A, second between world and country B. Then what I do is I sort this table by the correlation. So what I'm left with in FH is the correlations from the highest down to the lowest and the pairs that they represent. And this is this list of sorted correlations. It goes on further than this, but you can kind of see the pattern. And from this, we can then start to run our algorithms. So first, let's start with Prim's algorithm. The highest correlation is between the world and country A, so let's join those by an edge. After this, we've got country C and country D. Neither of those are connected to the world or country A, so ignore it. And move on to world and country D. So let's connect country D to the world by an edge. Country B and country C, again, not connected, so we can't do anything with that. Then we get world to country C and world to country E. And then country B to country D. So these are all connected to existing nodes that we have in our tree. So country C to country E, that would create a cycle, so we don't want to do that. World to country B, that would create a cycle. Country D to country E, that would create a cycle. So a little of stuff we can't do yet until we get to country C to bank C. So this looks like bank C is most closely linked to its parent country, which is interesting. The next one we have is bank D, so that's interesting. This bank is actually more closely linked to other banks than it is to its own country, as is bank E. And bank A, interestingly, is most closely linked to the world rather than to any particular country or to any of the other banks, suggesting it's perhaps a more multinational organisation than the others. That just leaves Bank B, which is actually just off the bottom of the list, which is most closely related to country B. So it looks like, apart from this mega bank we've got as Bank A, most banks are either connected to their home country or to other banks, and most countries are most closely connected to the world rather than to other countries. So let's look at Kruskal's algorithm instead. The first one we have is the world to country A, of course. And then we can link country C to country D. It doesn't matter that they're not connected, because next we can link world to country D. Country B to country C, that's fine. World to country C, that would create a cycle. World to country E is fine. Country B to country D would create a cycle. We'll have a lot of cycles there. So next we have is bank C to country C again. And then it starts looking familiar. Bank D to bank C, bank E to bank C, bank A still connected to the world, and bank B to country B. So you've got some differences at the start there, but it's actually fairly straightforward. And if we do a little bit of reorganisation, we can see that the results we get are reasonably similar. The key differences are where country D sits. So country D was linked to country C in Kruskal's algorithm, linked to country B in Prim's algorithm. So country B is in a different place, and country D is in a different place. But the broad structures aren't that dissimilar. So you can see there, this is how we can create a a vine copula structure in practice, and it's reasonably straightforward. I mean, the hardest part about that is calculating Kendall's tau, which is just a pain in the neck, really. But you can see it's not the hardest thing in the world. And clearly, if you had more variables that you're looking at, then just eyeballing the correlations is probably going to be suboptimal, and you want to start putting together some algorithm to calculate that for you. But you can see the number of correlations that you have, and the fact that we are using a greedy algorithm means that it's going to run pretty quickly. So anyway, that's where we're going to leave it for now. I'm going to start diving into the maths a little bit next time. I'll start off fairly gently, so hopefully you'll be able to follow it, and look forward to speaking to you next time.